a spot of training for when Sean and Roger retire. And I don't know why I'm whispering.
Because this isn't the headquarters of any secret organization. This is quite simply a story about high-technology roofing. Because this rather unusual dome is just part of a future business center. When it's finished, it'll offer as its centerpiece this remarkable conference room. And this is where I reveal that I'm not just wearing these sunglasses to look chic. They are, of course, a vital part of the explanation of the story. You see, when you build a huge glass dome like this so the delegates...
With a lot of people that are working on it, eventually the dream comes true. I'm not so sure if I like all the dreams I've had. This particular one is a building called a model train building in England, which has housed supposedly the world's largest model train exhibition. And I've had some other funny dreams. This is Lord Montagu had a dream of a multi-screen projection cinema, which I participated. Most of the buildings I've dealt with in the past, oddly enough, have been in the domical areas, and I've gained somewhat of a reputation in that area, and been called in on a number of projects where architects want unusual structures and unusual technology. This is a model of a building that I worked on in 1982, which is in Lausanne, Switzerland. It's the Lausanne Polytechnic. It still hasn't been in construction at all. In fact, this particular design was later dumped because the original head architect for the Lausanne Polytechnic felt it was too way out, or made his buildings look a bit too dull. But the thing that was raised in this particular project, which links into what one has about a dream, was the criticism was that in this large structure with all this glazing, what happens when the sun comes out and it's sunny in the summertime, and even in Switzerland obviously it's quite sunny, and the building overheats, or it's too much glare for people to be able to see properly. And this started me thinking really in a number of areas, technology, as to how one could adapt to this, how one could adapt glazing so that it would change, as much as the glasses that we have that change their color to adapt to the sun's photopic radiation. So this next, what we're going to put on now is this videotape, is really very apropos in terms of a dream, because it was a film done by the BBC.
This is Inspector's headquarters. Problem is, we can't prove it.
Hold it there a minute, sir. There's something suspicious about that roof. Can you enlarge that picture? Since when did a 19th century mansion have a dome like that?
All right, McCann. I think it's time for you to pay Spectre a personal visit.
Doing a spot of training for when Sean and Roger retire. And I don't know why I'm whispering.
Because this isn't the headquarters of any secret organization. This is quite simply a story about high-technology roofing. Because this rather unusual dome is just part of a future business center. When it's finished, it'll offer as its centerpiece this remarkable conference room. And this is where I reveal that I'm not just wearing these sunglasses to look chic. They are, of course, a vital part of the explanation of the story. You see, when you build a huge glass dome like this so the delegates can enjoy the sunshine, it's really not a lot of good if, as soon as the sun comes out, the whole place turns into a sweaty greenhouse. So what they've done is to design a roof which actually reacts to the sun, rather like these photosensitive glasses. But in the case of the roof, instead of changing with the sunlight, they actually change by heat. This is just one of the panels. And this hairdryer is representing the heat from the sunshine. So as soon as I turn it on, it should begin to go opaque. There it goes. Starting to spread across there. And very soon, no heat can get in, so the delegates will stay nice and cool, and they won't even be dazzled by the sunshine. And if you look up at the roof, you can see exactly where the sun's been shining this morning. It's a little bit like an artificial cloud. So, what better way to explain it than to use an umbrella? You see, inside each of those panels is a special liquid. And when it's cool, the molecules naturally cling together around a central point. But when it gets warm, they still stay clinging to that central point, but now the molecules are so spread out that they cut out the light waves. But it's not only the sunlight that turns it opaque. Inside each of those panels are lots of tiny wires running through, exactly like the rear window heater on a car. All those wires are connected up to a microprocessor, which gauges exactly how much heat is needed to turn each of those panels opaque. At the moment, for instance, we've got it to darken out those two panels up near the top there. And when it's all finished, the chairman can sit downstairs here in complete comfort, and when he wanted darkness in the main conference hall, he could have it at the touch of a switch.
Welcome, Mr. McCann. I've been expecting you.
Back to you, Roger.
James, do you know what this is? Well, it looks like a fabulous...
Well, I thought that would amuse you. That was a small program done by the BBC on called Tomorrow's World, which talked about this particular project. It was just before it was completed. And really, it leads me into, again, the dream of some individuals about this particular building. The idea of the architect, who is Lambert Gibbs, by the way, who died shortly after this project was completed, I think from the stress and strain of it all, really had some remarkable ideas as to what could be put. Remember that England is fairly conservative in what it allows for planning. And so their idea really for a conference center near the Heathrow airport, they went to a location which was something like 3 or 4 miles from Windsor, which was in the flight path of Heathrow, by the way, which we'll talk about later. But they ended up getting essentially a mansion which had been run down. And in order to get it through planning permission, they basically had to keep the entire exterior portions of the building totally intact. In fact, they renovated the entire building on the outside. But ostensibly, aside from a few rooms, they completely gutted the entire structure. And so they built 110 bedrooms, this conference main hall, which is seats almost 1,000 people. And it has some unusual properties. One of the ones is that the floor, you can see it here in this floor here. Wasn't given a pointer, but you can see it actually is in up position, where here the floor is in a down position. And there's no it's sort of hydraulically moved up in position, and bolts come in through the side, and there's no pillars or anything below it. So it can be locked off into two types of spaces. And below that, when this floor is up in the air, a number of different kinds of room configurations can be made. So, depending on what the client's interests are. His concept also was that the central meeting area would ostensibly be daylit when needed, and be able at a press of a button to darken out and virtually complete theater darkness would be achieved. This is something that really was already out in the bulletins for the conference center. As you're probably aware, a conference center has to have a lot of lead time before it actually opens to get clients to sign up. And so these technologies, or this concept, was already in all the literature for the place long before they even spoke to me. And I was ostensibly brought in for a completely different problem, in fact. Let me just show you the exterior of the building. You can see it's quite a very interesting looking one. You look at some of the beautiful brickwork here, which I found quite interesting. But the fact is that this particular building is in the almost direct flight path of Heathrow. And the General Electric, who sold the clients on this particular plastic polycarbonate, which you probably are familiar with, they claim that it had the same sound attenuating properties as normal glass. And when the acoustical consultants came in and found out that they were using polycarbonate panels, only double glazed, they drew up the alarm signals because the amount of attenuation would be not sufficient for people to be able to hear due to the position of the jet planes. And so basically I got a phone call saying, well, we've got this structure going up, and we've got a real problem with the actual sound attenuating properties of the dome structure. And so I brought my trusty team of people and we came up with we came up with a material which I had been working on for its thermal properties, and it turns out it had remarkable acoustic properties. At the frequencies which were most important, at the low frequencies, it was able to have the same sound attenuating properties as a 6-inch concrete wall. And it's quite a lightweight. If you have a sample here, you can see what it looks like, and it's just a lightweight panel. So we were able to achieve that goal for the architect. And he thought this was so good that he said, well, we've got some more problems. And that is the one which we talked about, which is the, I'll just show you a few more pictures of these particular panels that are going up into this dome. The dome itself, by the way, was designed by another individual, and I don't think it's a very good one in terms of its geometry and its structure, but be that as it may, let me just, you can see here each of essentially there was 500 and something panels, each of about 1 meter by 2.8 meters high. And each of these were tapered with various discrepancies in sizes. We had to be able to fit these what's known as hypercell panels, the acoustic panels, in between here, and ostensibly in a friction fit, and took quite a bit of trouble to get it to work properly. Each of the panels also had a special type of fiberglass developed by Pittsburgh Corning that acted as a fire barrier, so that if one of the panels caught on fire, then it wouldn't spread throughout the entire building. And here's one being made up. You can see a template that was used. We also developed another bit of technology for them with a number of corporations. This, you can see in each of these panels 2 discs. You see that the original designer of the dome didn't take into account that when you don't use a hermetically sealed double glazed unit, that you have condensation problems. And so if we had to come up with something in a matter of weeks that would solve this problem in an inexpensive and elegant way. And I went to, one day when I was out running with my Gore-Tex suit, I said, well, Gore-Tex is breathable and it's waterproof. So I got on the phone to W.L. Gore in Maryland and said, well, would you like to make up a special type of Gore-Tex membrane to be used on this double glazing? And they couldn't believe that I was for real until I flew over there. Obviously, they realized that I had enough money to come down there. Maybe I was not a crazy person, and showed them the actual project, and they agreed to do that. And 3 or 4 weeks later, they put a research team on it, and were able to come up with these small discs. They're about 1 inch in diameter. And the first versions that we tested out, they had some delamination problems, but since then, now they've been up for over about 2 years, and so far they've held up, and with no condensation problems at all. The third area, which which we addressed was the glare problem. The initial idea of the architect was really just to have essentially a pram hood that went over the entire building. And due to the constraints that we found later, the construction constraints and various other consultants that we brought in felt that it wasn't workable, we looked at what other ways of controlling the daylight coming into the space. The earliest ones that we had were, if you put the light on over here, the earliest ones that we had were really with film versions. And ostensibly, they were developed over a 10-year period by a company. Can you hear me? Yeah. They were developed by a company that's called Solar Sunstill on the East Coast. And this is one of the original samples that they sent me. Basically, it's temperature-sensitive film, and this one is, in fact, if I put my fingers on it for a while, the heat of my hands will leave an impression, hopefully. It still works. And basically, the idea we had for the glare control was this film. It's starting to go hot. I'll just heat it up a little bit and speed up the process here. Probably can see it's starting to change. It's going white in spots. Can you see that? And basically, we made up, in fact, because of the constraints, of the time constraints that were on this job, ostensibly, I received the mandate to go ahead and try and develop a system in January of '83, and we had to, at that time, they wanted everything installed in something like August of '83. So it was a ridiculously short time. So a lot of things were done in parallel. In other words, we had 3 or 4 things going at once, different technologies. The thermochromic technology, in fact, was only one of many mechanical systems and various systems that we looked at the same time, try and meet that type of schedule. And what we felt was, after a while, we felt that the films would probably work well for glare control, but certainly we didn't think that they would work for a blackout mechanism. They just were not dense enough, didn't have the opacity that would. And so really, we presented something like 10 different mechanical systems that we felt would do the job better. This we felt would be very good for the glare control, but for actually blacking out the facilities, we didn't think they would work. And the architect rejected all 10 of them. He just didn't like any. He didn't want anything on the inside of the dome. The ones on the outside didn't work. Everything we presented to him just didn't meet his fancy. And so I decided, to try and look at something else, which is really increasing the amount of thermochromic fluid layer. This is actually almost a solid in this particular case. And by increasing the size of it, maybe we'd be able to achieve the darkness that was required by the client and the architect. And the early versions that we had of these panels, in terms of the chemistry and in terms of everything, didn't look very good. You can see in this particular case, this what we call worming, that this is in a supposedly darkened state. Things started to separate, it started to break down. And the chemistry development at that point with the company on the East Coast, although they had 10 years experience, they didn't have any experience in making these kinds of thick layers or fluid layers, and basically everything had to be done from scratch in a 2 or 3 month period. We also had to find some ways of encapsulating these fluids, and I had with me one of the best model makers in Europe, and every day he'd go back and try to make a panel that wouldn't leak and it would hold up. And I think we must have had 30 or 40 failures before anything got. You can see some of the different kinds of strategies that we had, and even the quality of the materials was just not very good. Here's another one. Let me go back to this one. You can see here that this is actually a structured plastic sheet, and I guess you can see there's a dark layer. Of course, there's irregularities, but you see the white layers, the light layers, white strips, regularly through here. This was a problem of light going through there's a fiber optic effect on a structured sheet that we weren't able to eliminate. So we didn't particularly like those sheets, but at least they were able to hold up to some extent. And eventually, we were able to solve the chemistry problems. In something like May or June of '83, we were able to make some breakthroughs, and we were able to find stable chemistries that were able to work. We ended up in one of our tests, one of our early ones, with this thing we called the blunderbuss solution. It was something like 3/4 of an inch thick, and we all laughed about it. And then in the end, we actually had to use that. We had all these things with multi-layer effects and various other elegant solutions, but the blunderbuss of just really thick amount of thermochromic fluid was the one we ended up using. And ironically, it was because of this particular panel, it was so thick that we were able to get the building code approval on the other panel, which is the acoustic panel, because we had significant problems in producing that as well. We started to try and make it in polycarbonates, which were acceptable to the building code people there, and we couldn't do it. We were only able to do it in a polystyrene butadiene material. And it turned out that we had a fire test done on this panel, in fact the entire assemblage, and we were able to, it took 27 minutes to burn through on a horizontal burn test. This was done with the fire people and the building code people looking on, and of course I was keeping my fingers crossed that it would all work well. And it turns out it's a remarkably fire retardant panel. And here you can see pretty much the quality of the if you compare it to the ones before. This is showing a heating element, a heater behind here blowing onto you can see the whiteness of it and the quality of the transparency. Again, there I'm standing there with a heater over here. The idea really is to get it as opaque as possible, and we were able to get something like 120 to 1 ratio between its clear state and its opaque state. This just met the specifications by the architect, by the way. Here's a panel that's just sitting on the outside, and the sun is changing it. And this is compared to a 90% reflective white paint. You can just see it's a little bit, it had about a 75% reflectivity. So there was room for improvement. Now I'll show you the whole assemblage. Starting from the outside, you had this 50% transmitting gray polycarbonate, which was chosen by the architect right from the beginning. The hypercell, it's not very bright, is it? The hypercell panel, which was your thermal and acoustic insulation. The thermochromic panel, which had fluid in it, and it also had, as you saw in the film, electrically conductive lines on it that was silk screened on both sides, which could be used with heating. They provided the heat to black it out when it was required. And then there was an IR shield, which is not shown here, a film that was made by Southwall especially for this project, and then an inner glazing. The entire assemblage had about a 12 to 15% transmittance when it was clear, and 0.08%, something like that, when the panels were in the occluded state. Here's another shot of it. You can see the gray lines of the heating elements on this panel, and I have one here that I'll demonstrate later when the slides are off. This is looking into the dome, looking at all the thermochromic panels installed into it. And you have to remember that we had, if these were just square panels or some similar single size, we wouldn't have had so many problems, but they were all kinds of different shaped panels. And that created a significant problem in a prototyping stage when you're dealing with close to 5,000 square foot of glazing, of which 535 different panels. And that's a shot of the panels installed on the barrel vault section of the dome. This is looking at it, detail, looking through the actual fluid and into the hypercell, and you see they're very clear. Here are some shots. This is the dome. One of the things that we found, and it's really very hard to do with the slides here because the slides really aren't color corrected to a sufficient degree to be able to show this properly, but there are slight differences in coloration. You can just see a bit here. Can you see the light on that? It's not really working very well. Just look here. You just barely, you see slight differences in tinges in the building. And this is much more yellow than it actually is. I have some color photographs here that I can show you later, large ones that give a better color accuracy. But that was one of the things that the human eye is incredibly sensitive to differences in gradation and color. And the major criticisms of the system really came from that viewpoint. Let me show you some more shots of it changing. Here's the same section, the barrel vault, when it actually was in the occluded stage, or semi-occluded stage. And I just want to draw your attention, this was the black hole of Calcutta panel, which we eventually replaced. But we found just slight changes in the coloration. Here. If you actually took those panels out and looked at them, they looked virtually the same. But due to the multiple layer effects and various things that occur, these are white panels in really a neutral color environment, but they take on different colors. And we found that there was, depending on the sky color, depending on the position of the sun and the time of day, they would either look yellow, orange, they'd look gray, browns. And they not only did that, but they would change in a very abstract way. And I would say about 50% of the architects that looked at it didn't really like that. But you can see it up here, this transition period for about 15 minutes or 20 minutes when the sun came out, because it worked in both a passive and active mode. It worked to control glare as well as being pushed by a button. This was in the passive mode. So when the sun came out into this particular position, and we set it for being above 200 watts per square meter, whenever the sun was bright, ostensibly, that section of the dome was darkened out. And it took a while before those panels reacted, because they were very thick. And you can see here, this is the shading effects of the actual structure itself. So these panels weren't, this part of the panel wasn't going out, and this kind of abstract. However, in reality, it worked very well. I mean, there was no glare problems. There's ostensibly no solar heating problems. For instance, when this building was singly glazed in the springtime, when we were working in there was 130 degrees Fahrenheit in it at one point. On a clear, sunny day in England, which does occur sometimes, it was 130 degrees Fahrenheit. Under the same conditions when the system was installed, when I measured it, it was 72 to 74 under the same conditions. So it did remarkable well. The daylighting levels, and they were controlled between 500 and 1,000 lux, 50 to 100 foot candles on a constant basis. And although it looks like the panels to one side are a different brightness than the other, for instance, I bet you think that this panel is darker than that. In reality, they're not. And when you go up and measure it with a light measuring device, it turns out that they're really about at the same level. The eye it's very hard for the eye to spot differences in intensity between different colors. This shows a shot of what it looks like from the outside, and you can see this area here has been set off, and it's white. These are the discs that I mentioned before that control the condensation in the panels. Here's a close-up on that. You can see straight through here. You can see the white discs, the hypercell here, and in this particular shot, the thermochromic layer, which is highly reflected. Now on the inside, that will look like probably a burnt orange or a brown. So it's quite interesting, the differences in color. And here's a few more shots. This is showing the building in its ostensibly completed phase. And this is an interesting shot of it, the shapes of what happens here. You can see also these are two, this is a bad panel here, that's a bad one there. There are some leaks in those panels, which is a major problem that we've had on this building. The differences in intensity of the panel, the way it behaves, the eye just picks them up very dramatically. And although from a physical standpoint it works very well, it really requires a lot of more sophistication to be able to meet the standards that the architectural profession really would like. Some people like this flowing, and of course even the roof line, there's a roof line behind here, and it's picking up the shape. In fact, I don't know if I have a shot of it, but it picks up the shape of the roof line in one of these pictures. Not this one. There's another shot of it. This is again a different color quality. And another one here. You can see this funny jag up here is following the shape of the roof on the outside, which really goes up in a strange configuration outside the building. And you'll notice also that it goes extensively in sections. This particular set of panels is separated from that, and the position of the sun just only sets these sets of panels off instead of the ones above it. Here again is an interesting shot. You can just barely see, and here this is starting to go up, these smaller panels up on the top. And again, it's that almost an abstract painting quite quality that some people like and some people don't. I don't know. I haven't made up my mind, actually.
You're supposed to like it.
Am I?
You're selling it.
Well, I'm not selling it. This was where we actually just set off one panel by itself. This panel here. These other parts are being heated because of ostensibly the energy that's being put into that. Just an isolated panel being set off by itself. This is showing an interesting stage where you can see the differences in light quality from. This is just with the hypercell acoustic panels, then with just the fluid panels, and then sections of it are being set off. And in reality, when you looked at this area, of course the camera makes allowances, but you could not see properly. This was without these protective panels in place. And your eyes were totally blinded without the system installed. Fortunately, it didn't come out. Well, what were some of the problems that we had? We found that in about 10% of the panels, we took this system in, we put the system in and took it out 3 times. We worked, 24 or 36 hours straight at times, 7 days a week. I think I worked for a year and a half. A lot of people did that as well that work with me. And one of the things that we found is that we found in 10% of the panels we had this platelet formation in chemistry. In other words, 90% of the panels never showed this problem, 10% of them did. It turns out that we believe there's a contamination. We made 6 tons of chemicals under very quick conditions, not really laboratory controlled conditions that I would like, and some of the batches were contaminated. And we found that if you're familiar with the term pH and pH balance, what we found is that in these particular panels, the pH for some reason dropped, and these platelets formed. And if you we found that we injected something which brought the pH back to balance, and these platelets disappeared and the panel functioned properly. But you can imagine the feeling when you had something like this occurring. The other things that we found was that when this also occurred, this pH drop, then the viscosity of the fluids would drop. And there was essentially, which I'll show you an actual panel here, there was a very small seal, 2 places on the panel that were susceptible to leakage. And when the temperature rose up and when this particular thing happened, then we had leakage of the fluid from the panels, which when it really occurred on a large scale, which it did in a few panels, would actually come out through the dome and drip on the people below, which was not particularly liked by the clients. I think with any kind of brave technology like this, you're just really running you can run the gambit of things that can happen. The other thing that happened was that one of the batches of, this is ostensibly silkscreen inks, and the company that had helped us with this was Atchison Colloids. We believed at the time had done this thing many times before. You just talk about, looking at silkscreen inks on windows and various other things. We thought this was a developed technology, but it turns out that nobody had ever done it on polycarbonate before. And in the process of providing us with a specialized inks, which first of all, by the way, didn't work on polycarbonate, as they said it would, when we found that that one of the batches that they sent us, which was actually about half of the entire panels, had a flaw in it, and that there would be small spots of locations where there was ostensibly a lot of resistance or a breakage in the lines. And of course, when that would occur, and which didn't occur until about 24 hours or 25 hours after the panel was up and the heating system was on, then it would arc. In fact, at nighttime you could go and you could see little 1,000-degree arcing. And of course the panels could hold up for a while with 1,000 degrees C, but eventually they would burn a hole through the panels, and then you would have a second form of leakage. So that was another thing that we took all the panels out, in these various times that we put them in and out, and we were able to salvage a lot of those panels, but some of the ones we couldn't salvage.
What was the budget?
The entire part of the thermochromic budget was for everything, including the installation, was about $350,000, something in that neighborhood. That was for developing the technology, making it, and putting it in. And so that was another problem that faced us. We also had, so what we tried to do with this system was we developed a secondary set of panels, which were more known technology, which were small heating elements. And these went on the bottom of the coffer to stop the amount of power going through these particular panels, so that we could reduce the incidence of this burn through. And what we found with those small little heating elements that was made by a Scottish firm is that they got very hot. They were up to about 80, 90 degrees centigrade, which is close to boiling. So we had to lift the panels that were on the bottom of the coffer up. And of course, in doing that, we were letting light through. So we had to find a way of dealing with that as well, which was quite an interesting problem. All right, let me just see what some of the other things we have here. I just thought I'd show you some of the other architectural aspects of the building as well, and then we'll get on to the demonstration. This was in the foyer, and it's not, as I said, the color accuracy is not good, but it gives you an idea of what some of the building. This was in the restaurant area. And this is there's another dome structure which I was involved with as well. Which was a real headache because the shape of the thing was incredibly difficult to make, and that's inside that extra structure. Some of the things done architecturally here, I really can't. I didn't always agree with mixing of this building, the old building with the new, was sometimes done well and sometimes not done well, but I think it was an extremely ambitious project. I've been certainly proud to have worked on it. I'd like to go right over now to the demonstration of some of the materials themselves. Let me just get that off. This is I have 3 panels that I sent over here, one of which is being used by Professor Gaboni at UCLA, which was the best one. And this particular one, which was very much battered by the plane journey, but it's somewhat intact. It's not, some of the fluid is out of it, but it's somewhat intact, and you can basically see it. You can see the bus bar here, the electrical bus bar. It's actually on both sides, and these silk screen heating elements. In here, this white sort of tube is a crush chamber. We had to take into account the different thermal expansion contraction problems of the panel. And there's sensibly a little air hole that goes right into here, so from this end through so it allows this to sense. This is actually open to the air, so there's a seal. This seal probably had no problem with, but there's on this edge is a small little opening, which at this distance you probably couldn't see. It's only about the size of my finger, ostensibly. That's where we have a little stainless steel or polycarbonate grub screw that goes in here and seals it all. And this is where we had a lot of the leakage problems. Anything that we tried to use, Teflon tapes, everything that we tried to use, nothing sealed this thing off. And it really was in reality, this has been the real kicker of the whole thing. That particular small seal here, we've had it operating for something like 11, 12 months, and really right now we just basically took the whole system out to try and see if we could come up with a different panel design at this point. The system worked well in terms of what it could do. It can darken out the facilities quite well to what the level of showing slides that they required at any time of the year, and it also totally controlled the daylighting aspects of the building. As I said before, it was a constant amount of daylight from anywhere from 50 to 100 foot candles, controlled throughout almost all the different types of lighting conditions. And it can totally control the amount of solar gain. We measured it coming through under the worst conditions. We had something like a 3% shading coefficient, or something like 5% of the amount of radiation from the sun eventually was able to get through in terms of total amount that got through. So it really worked very well. Let me just heat this up for you. This may take a little bit of time. Starting to go now. Let's see a spot. Can you see it turning light? Unfortunately, the mass is so large that it's difficult to get it to move very quickly. If I take that off now, you can see it going back. Basically, it goes off at 30.5 degrees centigrade, about 90 degrees. And we set this, luckily this was set pretty accurately, so that it functioned exactly as we expected. The whole technology of thermochromics, and we're not the only ones that have worked in it, it's still very much an infant stage, but I think I probably have as much experience in how to set the temperatures of these things in response as anybody in the world. In fact, other than one particular project that was done in 1960 at the Munich Zoo, which is a small panel that was used then, this ostensibly is the only project in the world that's ever been used on, and it's never been more than ever a couple of square feet of this material ever put up. So, yeah.
What is the chemical?
It's proprietary. It's quite a complex chemicals. It's actually about 15 chemicals, and it is a proprietary, it's a patent pending material. I'm actually a co-inventor of it, and I was lucky enough to mix a couple of things that that happened to work.
Does it actually get solid in there? When
no, it stays a fluid.
still fluid even though it gets darker?
Yes.
It's not a crystalline.
No, it is a fluid in this particular case. Now I'll show you another version of it. You can look at it in more detail. There's not that many people here who can look at it a little bit more detail later. We've also looked at some window versions of it. This gives you an idea of the clarity. It can be made very, very totally neutral, spectrally neutral. This should act as a fashion. The thin layers are more sensitive to differences in these are quite cold, so they have to go up to 90 degrees Fahrenheit before they'll go up. It's starting to go now. You can see it now. The idea really is to get as high as light as I'll go back. What we found when you get to the thin layers, you have to raise the viscosity up quite high, or else you get ostensibly, when it goes in the reverse stage, like the other one goes back quite nicely, these tend to go back with a somewhat of a residue for about 20 minutes before they change back to being totally clear. And if you raise the viscosity up very high, then that phenomenon doesn't occur. This fluid in here is about 2.5 years old, so it's quite old. It's a little bit 2 years old. Sorry, it's 2-year-old fluid.
Is that fluid toxic at all?
No, this 2 years because it's coming up to be so it's a little bit less than 2 years. So this is May of 1983. So is it toxic? No, it's not toxic. You could put it on your hands and you could work with it, and it won't affect you in the least. One of the things that I tried to do was to make sure that every one of the chemical groups that we used was totally safe for human contact, and everyone have long histories of being used. Some of them, in fact, is actually used in the cosmetics industry for washing hair, things like that. So it's got a very good safety record. And you can see here this phenomenon which I mentioned before, which is this slight precipitation, which doesn't occur it won't show up in that type of panel, and it won't show up in this type of panel if we use a high viscosity version. But this takes a while before it goes perfectly clear.
Excuse me.
Yes.
Have you ever, experiments found any way to get the gradations from complete transparency through to
Yes. Yeah.
It's going to be very nice.
These are not totally opaque. The fact is that they can be designed to have a slope. In other words, as it gets hotter, it lets less light through.
Yeah.
All right. That's already. In fact, we can do not only that, but we can make step functions between such and such temperature. You can have that much light coming through. Yes, that we can do already. That's not a problem. All right. And are there any questions about this particular materials? Or?
How did those dots control the condensation? I don't understand.
Excuse me?
How did those dots control the condensation? I don't understand.
Well, they're breathable material, and of course the system itself is being maintained at a certain temperature, but it's computer controlled and it has heating elements in it, so it has a positive vapor pressure. The temperature of it is always going to be higher than the outside air temperature typically. And so basically you've got a vapor pressure which is higher than the outside air, and it just any excess moisture just goes right out. And the size of those is sufficient for the to be able to maintain dry conditions under any. Of course, they're waterproof. You can put water in them. Like if you took a cup of this stuff, Gore-Tex material is ostensibly a totally waterproof material, but it's breathable. So it lets the water vapor out, but won't let rain condensation. If, for instance, for some reason the system went below the air temperature, then you could get a reverse process occurring, but it's not very much. The flow is, yes?
How does that, the dome that you showed, where the direct sun hits the one side,
Yes.
it turns opaque. Say the northern side or the
Well,
top side, it's not going to get that severe of heat. Is there still a heat gain, or is it pretty cool?
well, basically it tries to even out the amount of daylight coming in. The system ostensibly tries to get equal amounts of light in all directions. So you have some of the energy from the sun is changed to long-wave radiation. And what we have in there is a infrared reflector that was on the inside of the plastic diffusing element on the inside panel. That was ostensibly inside this, on the inside of this particular panel. And so whenever this absorbed, even this absorbed some energy, that long-wave radiation would attempt to get in, but was blocked, or most of it was blocked by this infrared shield. So even on the north side, it was with a U value of about 0.9 in the SI units, which I have to change over. Let me just change it over to the 0.15 in the BTU. It had an R value of 6, all right? The whole assemblage is an R6 insulation on it, a little bit more than that. So it doesn't take much energy to keep that the climate controlled there with that amount of insulation, which is something that leads me to the.
So even with the opaque side, you were getting the same type of light from every side, you said?
Yes.
Even through the opaque?
Yes. It's not opaque. In the glare control mode, in the solar control mode, it has a different amount of light intensity that comes through than if it's electrically induced typically, except on a very sunny summer day. Then it will get as dark as if it was the heating elements. But typically, it will just control the amount of light from all directions so it's even. And it worked very well.
You said it was installed for 11 months and now it's...
We're taking the panel, the thermochromic panels out. We're still waiting to see how we can solve this leakage problem. We feel that we're trying to find some ways of, when the panels were made, there were some things which were shortcutted in their manufacture because of the time. The first version of these panels were only made in November of '83 and it was installed in January. The actual first physical prototype was made, 2 months later it was installed, these were made. And there was, in order to meet their schedule, we didn't beef up sections of the panel around here, which was in the original design. And once they ostensibly, if they're weakened in that section, and the temperatures that they're operating at, the cracks can occur. And it's very difficult to fix them once they're cracking, so we had to take them out eventually. I don't think really the polycarbonate is the proper panel for this job, and we would like to replace them with something else. But right now we haven't decided what we're going to replace them with. So ostensibly the system's out in that regard.
It's the same material in the other one, the polycarbonate.
This is not polycarbonate.
No, the clear one.
This one is glass.
It's glass.
Yeah, well that's the best.
That's best. It doesn't have heating elements in it, either it does.
No, this doesn't have heating elements.
It's the glass with just the
yes,
chemical in it.
yeah. And I frankly, other than I'm heavily boxed in by trying to solve this problem for them, I frankly think that this technology is much better suited for just a passive mode, not using it with the heating elements. I don't really like that system at all. I think it uses up energy. But in the passive mode, I think it's quite. I just wanted to show you I have some figures here that I'll hand out with these technical figures, but just wanted to show you its performance compared to, for instance, glass and polycarbonate. Letter A is with 6 millimeters of polycarbonate with 220 millimeters of air and 4 millimeters of polycarbonate, which is what actually the system was before we put the things in. The actual measurements on B show at 250 hertz which is a critical peak for the amount of decibels for plane noise. It peaks around 250 hertz. You can see that it had an actual measured value of 31.5 decibel reduction, which is not particularly dramatic. Glass, which is number C, would do about 39 decibels. But the cost of replacing the entire glazing with double glass was something like 350,000 pounds. And so the system that we came up with, which was much less expensive, obviously, I think it was order of $60,000 for the whole thing. That's shown in letter E, which is about 49 decibels with that panel installed. So it's close to 50 dB in that range. And with these brochures I'll hand out, it gives you a more detailed description of in the other frequency ranges. It's basically, this particular panel by itself has a 36 dB reduction at 125 hertz by itself. And basically it just moves off. It's very good up to about 400 hertz, 400 or 500 hertz, and then just drops away. And if you combine it with the other panels, then you end up with a very good hybrid that performs extremely well. Why don't you put the next? I just want to show you also this particular panel and its properties. If one looks at the U value of something, I'm sorry, this is in SI units. You can divide by 5 point something to get it into BTUs. It shows the U value for one pane versus the transmittance, the solar transmittance. And this is for double glazing, triple for. The problem is that as we get to lower U values and more glazings, we lower the amount of light transmittance through it. And so this sensibly is able to handle that. You can see it's ostensibly the same as a 4-pane of glass, but with a higher transmittance. So it gives you so that this was also an integral part of the design, because we had to trap the thermochromic layer in between two insulating materials in order to get it to go off in the winter time in the English winter when it was bright and sunny. We had to ostensibly keep it away from both the cold exterior and also the temperature of which it was on the interior. And the next one. This shows it's compared to double glazing. This is in the British units, and shows it's also a function of the temperature at which it's at. We did a lot of studies on it because the entire system, in terms of optics and heat balance and everything else, really was a very complicated system, and it took a lot of playing with it, and even, for instance, I remember changing the amount of insulation around the edges, the taping of the edges of the metal structure. We had to just adjust the thickness of that very, very accurately in order to get this thing to work, exactly as we wanted to. The next one. I won't go through this, but basically found that the transfer mechanism is 83% radiation through here and 17% convective. Ostensibly, this acts as if it was a low emissivity film of about 0.25. In other words, it acts as an infrared shield itself, even though it has no metallic layers on it, just from geometry alone and the materials and shapes involved. This brings me to the last one, which I think is the most interesting thing. If we're looking at the value of glazing, traditionally, we've limited the use of glazing to a certain extent now, and with a new passive viewpoint. And in actuality, a glazing in virtually all directions can outperform an opaque wall, as long as it has a low enough U value. And what you have here really is these two lines represent the thermal loss lines, or thermal balance lines. Anything below this line represents something where you don't need to provide any energy. In other words, the window is ostensibly a energy giver, and above it, then it's a loser. If we look at the average temperature at 4 degrees C with single glazing, you can see on a typical cloudy day, it's below the line as a loser. You're losing energy. I reversed the sentence. And the only way you get to a very clear, above on an average day, this is, say for instance, on a south-facing glazing, you would get a net benefit. Whereas double glazing, you can go to much, on a cloudy day, you can just about break even, and on an average day, certainly you gain something in that temperature regime. This is where we're at with this type of system. And on virtually, even on a cloudy day, you're getting a net energy gain on the space, or a break-even point under most conditions. So ostensibly, it's saying that a well-designed glazing, from a heating standpoint, can really provide you with all the necessary heat for that building. The question then goes, what do you do in the summertime or in a large commercial building where air conditioning is the mode which you're really interested in? And that's where these two really mesh together, which is now ostensibly a control which can block out the excess solar gain whenever you need it. And some of the studies I've done recently, computer simulations and other studies from actual buildings, the aperture control is one of the most critical aspects of a building. If you don't have proper aperture control, you lose tremendous amounts of energy in terms of heating and cooling loads. If you, for instance, the application of this type of film or glazing onto a large commercial building would lower the cooling requirements something by 30%. So just a change of the glazing. Traditionally, a lot of people are not using shading devices on these large glazed structures. Nobody's using shading devices. I mean, is this an architectural objection to it? I don't know, maybe the cost or whatever.